Hello, and welcome to Chapter 3, which deals with exponential and logarithmic functions. So, so let's begin. 3.1 has to do with exponential functions and their graphs. And in this video, we're going to recognize and evaluate exponential functions with base A. We're going to graph exponential functions. We're going to use the one-to-one property. We're going to learn what it is. We're going to recognize, evaluate, and graph exponential functions with base E. And then we're going to use exponential functions to model and solve real-life problems. Okay, exciting. So let's get into it. Exponential functions. So far we've only talked about mainly algebraic functions, which includes the polynomial functions and rational functions, right? So here we're going to talk about two non-algebraic functions, the exponential function and the logarithmic function. So these functions are examples of what we call transcendental functions. Okay, so let's talk about what is an exponential function. An exponential function with base A is written as f of x is equal to a to the power x, where a is any number that is positive but non-zero and not equal to 1, which makes sense because 1 to the any power will just stay 1, and this will just be y equals 1, so that's boring. And then x can be any real number. This base a is equal to 1, well, I just said it because it just equals 1. That's a constant function and therefore boring. Okay, so you have evaluated a to the power x for integer and rational values of x. You've done this before. For example, you know that 4 to the power 3 is 64, and you know that 4 to the 1/2 power is the square root of 4, which is 2. However, if we want to be able to evaluate 4 to the x for any real number, we need to also include forms with irrational exponents. So remember, irrational, so 2 is irrational. 2 is approximated by this crazy decimal, 1.41, blah, blah, blah. So if you want to think about that, you can approximate square root of 2. And you can think of a to the power square root of 2 as this number that gets approximated closer and closer as you include more decimals that belong to the square root of 2. Okay. All right, so first of all, we need to go over how to, I know this might seem like, well, duh, this is easy, but let's just make sure we understand how to enter these in the calculator because we're going to be using the calculator a lot for these functions in particular. So here we have 2 to the x, 2 to the negative x, and 0.6 to the x, evaluated at certain numbers, negative 3.1, pi, and then 3/2. So let's look at this. Here are the keys that you enter. The only thing I would say is that in order to get to pi, you have to hit second. So let's look at this quick little video. So if you want to enter 2 to the power, you hit that arrow key and then negative 3.1, and then you would hit enter, and that's it. And if you want to go 2 to the power, little caret thing, negative, and then pi is the second key, and then that caret again. So see how pi is in blue? So second, and then the little key, and then enter. And then 0.6 to the power 3/2. So if you're going to do to the 3/2 power, you're going to use a little caret key again, but please enter parentheses because you want to be able to tell to make sure that it's all in the exponent. Okay, so that's it for that. So let's talk a little bit about graphs of exponential functions. So let's say I wanted to do this sketch the graph of each function, and we know I'm going to go through it with the calculator, and I'm also going to show you how to do it by hand. Okay, so let's say we have y equals, we're going to put 2 to the power x, so 2 caret x, little x key right there. Okay, and then on the second one, we're going to put 4 to the power x, so 4 caret x. And then we have to figure out what window. So sometimes I just hit zoom, and then I go to fit. Sometimes that works out very well, and sometimes it totally doesn't. So let's see how it goes. So enter. Yeah, that's not great. I don't like that. So let's do zoom standard, so zoom 6. That just gives us the regular 10 by 10. And I'm not perfectly happy, so let me go to the window and make the y minimum a -1. That way it starts lower. So I'm going to delete that. That's all I'm going to change. Hit graph, and look, beautiful. So now I can kind of see, they both hit 1 at the value of x equals 0. So the way that you would do this, the way that you would do this by hand, you would list a table and you would just go ahead and plug in the values, -3, -2, -1, 0, 1, and 2, and then you would get the solutions back for x. So 2 to the -3 is 1/8, 2 to the -2 power is 1/4, and so on. And so it would look like this. However, this is a shortcut, okay? So listen up. So if you had already graphed it like we did in the previous slide, all you need to do is hit second and then that graph, and the calculator will reveal a table with the data points all in there very nicely. So yeah, is that considered cheating? I don't know. I think that's just being smart. So just make sure you know how to do it both ways. Okay, so notice that both of these graphs are increasing. And here, if you plot the points, they're very close together. In fact, like here, they have the 1 in common. They both have, here they have 2, 4, and then 1, 4. So it's very close. Like they get close at some points. So then they're both increasing. So they go from left to right. They're going up towards positive infinity. Also, which makes perfect sense, the graph of 4 to the power x is increasing more rapidly than the graph of 2 to the power x, which makes sense. So at 1, 2 to the x is 2. At 1, 4 to the x is 4. At 2, 2 to the power x is 4. And at 2, 4 to the x is 16. Huge difference, right? Yeah. Okay, so let's just talk about what's the characteristics of the exponential functions a to the power x and a to the -x. Okay, so let's consider this graph here, a to the power x, where a is greater than 1, but not equal to 1, so it's positive. What's the domain? The domain goes from -infinity to positive infinity. What's the range? It approaches 0, right? It never crosses, but it's approaching 0, and it goes up to infinity. It does not cross the x-axis. Okay, so if you don't believe me, try and think of what value of x could 2 to the x equal 0. Okay, if you want to really try it out, think about it for a second, and if you found it, let me know because I'm very curious. Okay, so anyways, y-intercept 0, 1, right? Because any number to the power of 0 is 1. Okay, and it's increasing, yes. And the x-axis is a horizontal asymptote. So it approaches 0 as x goes to -infinity. And this is because a to the x, if x approaches -infinity, remember the negative is the reciprocal of that. So it's 1 over a, and then as it gets bigger and bigger, 1 over a increases. The denominator increases and therefore approaches 0. Okay, and this function is continuous. Okay, so what about a to the -x when a is positive, right? That's the same thing. You can think of it as this is a reflection across the y-axis, okay? So that's one way, and it's true. It reflects across the y-axis, so if you remember transformations. But the domain is the same, -infinity to positive infinity. The range is the same, 0 to infinity. The y-intercept is also 0, 1. -0 is still 0. And now the function, the big difference is that it's decreasing. That's pretty much it. It's just decreasing, and it's a reflection of a to the power x. And it's continuous. And also note that the graph of an exponential function will always be increasing or always decreasing. Okay, so as a result, these graphs pass the horizontal line test, and therefore they are 1-to-1. So what does that mean? That means you can use this property, 1-to-1, to solve simple exponential equations. So I think we've done a bit of this before in previous classes, but let's just refresh our memory. So you have an a positive that's not equal to 1, and it's the same base, and you have different exponents. If they're equal to each other, okay, and there's nothing else, surrounding the equation or anything, then you can also say that the exponents equal each other. Okay, so because this output is the same, the inputs are the same. Okay, so vice versa. Okay, so if you have x is equal to y, then you can also say that a to the x is equal to a to the y. Okay, so now we're going to talk about a specific base, call it the natural base e. Okay, this is an irrational number. E, it's approximately 2.71828, and it's really interesting. And this e to the x is called the natural exponential function. And if you notice, it has all the same properties as what we've just talked about, because this is a very specific case of a to the x. This is the specific case where a is equal to the value e. And what is e? Here it is. It's approximately 2.718281828, and so on. So you have to understand that e is this constant, and I think by now we've talked about this many times, that e is approximately 2.7, and x is the variable. So how would we use our calculator to evaluate function e to the x at each value? And the nice thing is that the calculator has an e to the x value, so let's look at it. So if you wanted to do e to the negative 2, it's the same. You find the e to the x to the power negative 2, and then enter e to the x, negative 1, enter, e to the x, 0.25, enter, e to the x, negative 0.3, enter. Now, just make sure in different calculators have different things. Yours might need the caret, the little up button, and some others might not. Okay, so you're just going to have to see what's your case. Okay, and then I'm going to get into applications. I don't really assign too much homework on this, but I do want to go through continuous functions and compound interest really quickly, because of course we're talking about e, we have to talk about that. Okay, so so let's talk about one of the most familiar examples of exponential growth is an investment that earns continuously compounded interest. So first of all, in general, the formula for interest compounded n times per year, okay, is this here, P, and then it's 1 plus R over N to the NT, where A is the balance in the account, P is the principal, right? The original deposit, R is the annual interest rate, and N is the number of compoundings per year, and T is the time in years. Okay, so using exponential function, we can develop this formula and show how it leads to continuous compounding. Okay, so suppose we invest the principal P at an annual rate R, compounded once per year. If that interest is added to the principal at the end of the year, then you have this new balance P times the quantity 1 plus R, because you have the original plus you have the interest of 1 year. So then if you keep going, so consider the following. So like for year 0, P is equal to P. For year 1, you have P times 1 plus R. For year 2, you have P2, which is equal to the previous times 1 plus R. So basically it's P, 1 plus R squared, because see how it's like based on the one before it? Okay, so it keeps going. So you keep going like this, and ultimately you get, okay, after T years, you get P times the quantity 1 plus R to the T power. Okay, so let's see, that's just once compounding once a year, but what if we compound more times a year, like quarterly, monthly, or daily? Then N would be the number of compoundings per year, and T would be the number of years. So then the rate per compounding would be R over N, and the account balance after T years would be to the NT, okay? So when you let this number of compoundings N increase, basically approach infinity without bound, this process approaches what we call continuous compounding. Okay? So you don't have to know this for a test or anything. This is just showing you how it developed. Okay, so let's say, for example, we want to let M equals N over R, okay, in the formula for N compoundings per year. So this, if M is equal to N over R, then we can rewrite N as RM, or MR. Okay, so you see here, we just replaced it, and we simplified the function to look like this. And the reason that we're doing this is because we want to show you how E comes into play. So that's, you don't have to overthink it. So if I was to keep plugging in values of M, notice what happens to this special quantity 1 plus 1 over M to the power M. So see here the output, as M gets larger, it gets closer and closer and closer. And if I take the limit, we haven't really talked about it, but as M goes to infinity, this quantity is going to approach the number E. So then we can rewrite this, and we get a new formula. A is equal to PERT, or PERT. That's kind of the way I remembered it. I don't know. Okay, so finally we can say, okay, so if I compound n times a year, I use this formula, A equals P times the quantity 1 plus R over n to the nt. And then if I compound continuously, which will be given in the problem, you just use A equals PERT. Okay, so here is a super fun example. We invest $12,000 at an annual rate of 3%. What's the balance after 5 years when the interest is compounded either quarterly, monthly, or continuously? So quarterly, it's a finite amount. N is equal to 4. So you basically just plug in everything. So 5, right? T is 5, N is 4, R is 0.03. The principal was 12,000, and then we basically use a calculator, and there it is. If you have a monthly compounding, that means that it happens 12 times a year, because N represents the number of times compounded per year. So then you can see, you just plug everything in again, and then you get what A is. And then finally, for continuous, you use this equation, okay, because we saw before that that's where E came from. Okay, we use PERT. Okay, and that is it for me. This is your homework, and please be on the lookout for 3.2, and I will see you on the next video.